Hello students, today our topic of the discussion will be the continuation of the performance analysis for spread spectrum communication systems, but today we will not consider the direct sequence spread spectrum system diagram that we were considering for the last 3 modules. Rather we will shift little bit to the receiver transmitter receiver architecture and the modulation technique. And let us consider today a quaternary system. What is a quaternary system and how the performance of a quaternary system will be changed with respect to the system model considered, and will be our consideration, and we will see today. Remember, received signal of a quaternary direct sequence spread spectrum signal, received quaternary direct sequence spread spectrum signal. If we consider there is a perfect carrier synchronization availed, and the chip waveform duration is considered to be Tc. I mean, exact code synchronization has happened, exact acquisition may be happening, code synchronization as well as carrier synchronization is done kind of. In such a situation, that received signal, which is also equivalent to my transmitted signal, because the wireless channel is not considered in between when we are writing this equation, that will be given by this expression. Remember, when we talk about a quaternary signal, the situation is such that we will have two different carrier signal which are orthogonal to each other, and hence they are devised from the orthonormal basis functions basically involved in this equation in a quaternary system itself. And we have also two different symbols transmitted over these two orthogonal basis function, and within that, actually once we are using the direct sequenced spreading, so the spreading signal that is involved to spread the symbol D1 is P1, and the sequence that is utilized to spread the signal D2, suppose it is P2. So, the situation is such that we have two orthogonal carriers to transmit the signal D1 and D2, and in each of these carriers the spreading sequence involved to spread the data signal D1 and D2 are correspondingly let us consider to be P1 and P2. We have loaded the power in such a way in both the orthogonal direction in such a way that the total power they are equally shared. The power of both the signals are equally shared and given by the square root of the s. And remember what is T0? T0 will be the relative delay between the signal received on the say cos axis or the one of the carrier with respect to that actually what is the delay, effective delay available on the other carrier. The signal received in one carrier and the signal received over the other carrier, if we consider that there is a relative delay between these two, so that delay will be symbolized in this derivation as T0. So, I repeat, in this quaternary system we have two carriers simultaneously carrying two different data symbols. The data symbols are mentioned here, symbolized here as D1 and D2. Remember, both of the signals are having dedicated sequence, PN sequence or any kind of the code sequence that of your choice to spread the signal, and there is a time delay also considered in between the signal received over one carrier to the signal received over the other carrier, and that delay we have modeled to be equal to T0. So, the received signal and power that we have actually sent, both are having the equal power before transmission, and combining all the effects. So, we are here given by equation 1.55, where the received signal ST is equal to given by this. Why am I saying that received signal is ST? Because usually we mention the transmitted signal as ST and the received signal as RT. In this situation, ST and RT are exactly same, considering the fact that you do not have any wireless channel suppose in between, you have in between the transmitter and the receiver as if you have a AWGN channel, additive wide Gaussian kind of the noise channel, which will add Gaussian noise, but it won't actually give any other kind of the effect of an wireless channel like the dispersion or the change in the phase frequency of the signal. So, that is not expected to happen, and so there is no attenuation also, the signal components will be visualized on the received signal. So, no effect of any other kind of wireless or any kind of the guided channel is considered, and we are thinking that the direct signal is received. And even in 1.55, while writing the expression for 1.55, we have not considered even the effect of the noise added to it. So, it is purely the signal generated in the transmitter and received at the front end of the receiver in absence of any kind of the channel, in absence of any kind of the noise. And in our consideration, when we have considered that the P1 and P2 are the two different spreading sequences, remember the sequences are different, but the chip duration for both the sequences are equal to Tc, and the rate at which the receiver is sampling the signal is hence 1 by Tc. So, with this consideration, let us understand little bit more about the kind of the modulation schemes that we are going to utilize here. If we utilize the QPSK, quadrature phase shift keying, for this modulation of this D1 and D2, remember in that situation your delay between these two will be exactly 0. But if you utilize the offset QPSK or you utilize a minimum shift keying MSK, that is a very popular scheme for the frequency hopping spread spectrum communications, then this value of the T0 will be equal to Tc by 2. So, for QPSK it is 0, but for MSK it is Tc by 2, and orthogonal QPSK also it is Tc by 2. So, you would like to choose the QPSK communication over others, but remember the cheap waveforms usually that we prefer to utilize. Let us finish that also. The kind of the cheap waveform we are preferring to utilize for OQPSK and MSK are like this. For OQPSK, the cheap waveform will be a rectangular type, and for MSK usually we prefer to use a sinusoidal signal. So, if you see the MSK spectrum of an MSK signal, you will see that the spectral side lobes for this MSK signal is actually very minimal for the direct sequence signal as compared to the QPSK or OQPSK. So, that is why actually the loss in the signal power, if you have a high spectral lobes, actually then you have to capture those lobes also inside the receiver to extract the signal. So, the less power you will be having on the side lobes, the main lobe power, the main part of the power signal power or the modulated signal power will be confined inside the main lobe, and in that situation actually your receiver processing will be actually easier, and your processing involve the capturing of the power from the main lobe of the modulated signal only. In that sense, MSK will give you the plus point, because most of the signal modulator signal power will be confined within the main lobe of your MSK, and the side lobe powers are heavily decreased when we are spreading is done compared to the orthogonal QPSK or the QPSK. So, we prefer the MSK signal to utilize, and remember there is another plus point over MSK, because MSK signal by default in the MSK signal we prefer to use the cheap waveform of sinusoidal type, and we all understand now the plus point of using a sinusoidal cheap waveform over a rectangular cheap waveform. In the main plus points we have already discussed in the last 3 modules, and the plus point and the advantages of this choice of this cheap waveform comes from the fact that you will get an extra dB band, extra dB gain on the symbol error probability, because the variance that is contributed from the interference that can be heavily diminished by an amount of 1 dB around. and it also the sinusoidal chip waveform. That is why in combination with the MSK, because MSK is giving a confined power within the main lobe and sinusoidal is allowing you to have a extra gain over the interfering signal at an amount of your 1 dB. So, the combination of MSK and the sinusoidal is the best preferred pair for utilizing in the direct sequence spread spectrum communication. So, in quaternary system we will proceed with MSK sinusoidal signal, and considering this understanding that the double carrier is coming in the receiver and with two different independent symbols. Let us consider a classical dual quaternary system. Dual quaternary system is having this D1 D2 independent as discussed in the last slide, and TS if it denotes the data symbol duration before the generation of this signal that we have seen in the last slide. Then actually TS1 will be the duration of the channel symbol. So, there is two different definition. The channel symbol duration consists of the two symbols D1 as well as D2, and each of them symbol duration is considered to be TS. So, the channel symbol, this is the channel symbol duration. So, channel symbol is considered with both D1 plus D2, and the channel symbol duration hence we will consider as TS1. The channel symbol duration we will be given as twice the TS, and as I have already mentioned that TC is the common chip duration for both the P1 and P2, but P1 is not equal to P2T, P1T is not equal to P2T. We have given different codes for the modulation, there is a code keying also you can think of going on. The number of the chips per channel symbol is now 2G, because G is the symbol number of the chips you are getting after spreading the number of the chips that you are getting per symbol. So, G is given for TS by TC for D1 corresponding to D1. Also, there is another gain involved with respect to TS by TC related to D2. So, if I see from the channel symbol duration, so the total gain we will get as a 2G, and over the gain of this 2G during the channel symbol period, you will be getting a total 2s number of the stuff divided by TC. So, that is why TS by TC is equal to G, and hence you are getting twice the gain involved in this kind of the communication. Let us consider that in the receiver the synchronization is perfect. So, the carrier synchronization and the code acquisition both are perfect, and based on that we will discuss the receiver architecture immediately in the next slide. And let us also consider that we are transmitting the symbol D1T, and which is equal to, and applied the decision based on that, and this 1.56 this equation, this once we are receiving at the end of the symbol interval, there will be a signal generated as V, and V will be combination of the intended signal, and then it will be a combination of the interference contributed, and again the portion will be contributed by the noise part. Let us first look into the receiver architecture. See, we are familiar with the matched filter based coherent PSK receiver architecture, where actually the single carrier transmission was going on. We have seen that after entering the signal, input signal to the receiver was RT, and it was then synced by the sync device. Basically, this is operation that is going on to bring the signal from the RF to the baseband, and so you need to synchronize it with FC, and finally, this is the channel matched filter or the chip matched filter, sorry, it is a chip matched filter where the we saw earlier that the match filter transfer function was matched to the chip waveform that you are transmitting. It followed by this match filter was the sampler. That sampler was sampling the incoming signal at a rate of the chip rate. Sampler and the locally generated your spectrum signal, they were actually in sync by the chip rate clock, and sampler also was responsible to generate the G number of the samples over the duration of symbol duration of Ts. And next comes actually the section of the despreading, where actually you are having a multiplier followed by a adder following the correlator architecture. And we have done our discussion in the earlier few modules that input to the adder circuit was Zi, and here is the V, the combined signal after the addition and the despreading, the signal V generated, which was entering into the decision device. And so here we will have, as we are having two different carriers, and the carriers are actually one on the sine and another was on the cos. So, we will have two independent paths parallelly processing in the receiver. The received signal is hence in this quaternary system will be multiplied with the cos 2 pi fct as well as sin 2 pi fct generated by the pi by 2 shifting of this synced signal. And so, here also you will here actually see from the top to the bottom we are having an extra block called delay, where we understood, we have seen in the expression that the another carrier is delayed by an amount of T0 with respect to the earlier one. To bring both of them in sync, here you have to introduce another delay of T0, and then you do the match filtering. Sampler is doing the same job that the earlier one was doing. And remember, now from here onwards, as you have delayed the signal another carrier by an amount of T0 to sync with the other carrier. So, sampler can be driven, the same clock circuit can drive the sampling of both the path, and the same SSG, the spectrum generating generated signal can be applied to both of them. The addition circuit like the upper one, they are identical in both the paths, and like the upper path, this multiplier plus the adder, he is contributing to generate the generate the despreading the signal. So, V, if I call it V, it will be also V dashed. So, they are expected to be corresponding to the data signal D1, and it is corresponding to the data signal D2. So, individually the decision is taken on the D1 and D2 on the upper path and the lower path, and once the signal detection decision and the detection is over, now here is a combiner circuit who will be doing the parallel to serial conversion, and these are the output symbols. So, in the output symbol you will get D1 and the D2 at the same time. So, it is a parallel processing to serial addition of the detected devices will be going on in the parallel to serial converter, and you can actually have output. Remember, this delay will be set equal to 0 if you are following a QPSK modulation, and if you are having a MSK modulation or orthogonal QPSK modulation, we understand that this delay is required to be set with TC by 2. So, and in the whole process we have considered that there is a perfect carrier synchronization. So, synchronization is perfect. Synchronization, by the term synchronization, I mean to say that it is a carrier synchronization followed by the code acquisition is done. So, there is no misalignment and hence the sampling, the SSG generation and your addition despreading, hence the despreading operation, and all are the time synchronized, and there is no offset also available in terms of the frequency between transmitter as well as in the receiver. So, this is a closed architecture of a quaternary system. It is just a scaled up version of a single carrier communication match filter based receiver architecture for single carrier communication that we have observed in the earlier modules. From here onwards, we will recap that we understand. I am going back once more, because in order to recap, we know that here was our sample value Z I after the multiplication, here was our value V dashed. Remember, inside Z I, as we are talking about continuously the interference, there was a contribution from the signal part and there was a contribution from the jamming part and contribution from the noise part. And inside V 1, so corresponding terms will be some contribution from the signal part and the contribution because of the jamming part and the contribution because of the noise part was involved. The corresponding expression for J I and N Y we will recall from the previous understanding. We have several times seen this both of these expression in the previous module, where our IT is the jamming signal, NT is the interfering signal, and hence like the earlier modules, RT is having a module like signal model like ST plus IT plus NT, and inside ZI the corresponding terms are called SI plus your JI, capital SI plus JI plus NI. The expression of this JI after dispreading operation, we have seen we can write it like this, and after dispreading the dispread noise can be written like this, and FC is our transmission frequency, carrier frequency. There is an important term here involved that we have not discussed in during the single carrier transmission. The term is called the crosstalk. This crosstalk is coming the approximated the expression that will be the contribution on the first one, I mean the P1 on the P1 due to the P2. So, P1T and P2T were the two dedicated spreading sequences given to spread the data symbol D1 and D2, though we understand, but finally you see that after the final decision both the signals are getting combined, the decision is combined. So, there may be a influence of if the choice of the codes are such that they will be having some interference, some overlapping between during the dispreading procedure, then the codes will, if they are not perfectly orthogonal in that sense, I mean to say that they have chosen in such a way they are partially correlated, and cross correlation function between P1T and P2T is such that it is the cross correlated output is not perfectly 0, even if when they are perfectly synchronized. In that situation, there will be a term generated called the crosstalk, which is given by like this. And this crosstalk will play an important role on the decision device. And for the lower decision variable like the upper one, we can write down the equation like this, because if we are transmitting that for lower one, the D2 symbol is transmitted and D2T is equal to D20, say symbolized as this. So, we will have a signal component like this, and we will have the contribution from the jamming part and we will have contribution for the noise part. Remember one thing, though you are processing parallelly for two different carrier signals, the contribution of the jamming signal and the noise signal will be equivalently added on both the path. So, the contributions from the jamming and the noise power can be equivalently treated as a way that if I know the contribution and the expression on over the one path, that will be simply replicated over the next, the contribution section from the combined effect of the jamming plus the noise. And this J1 dash and N1 dash, that is Ni dash, simply actually having some resemblance on these, they are basically the same, the expressions are basically the same that we have written for the upper path called Ji and Ni. So, there is no difference between these two, the same interfering signal interfering the both path, same noise signal is interfering and is getting applied on both the path. So, of the available desired signals, and the signal power S. If I understand that S will be the total transmitted signal power. As we are having two different carriers, the law is that we will divide the transmitted power equally over both the carriers, and that is why actually the component, this was the transmitted signal, half of the power will be loaded on the I phase and half of will be loaded on the Q phase signal. And we understand that TS1 is the total channel symbol period, which is equal to twice the symbol period, and we also understand that the energy then the per channel symbol will be given by capital S into Ts, because each of them are getting S by 2, and hence it will be getting totally the for the channel symbol you will be getting S by Ts. And hence for the direct sequence system with the PSK, the mean value of this V, will be coming with your d10 square root of S into Ts and mean value of the other part. So, it is the mean value of the V is considered here. V, by means of V, we are thinking that we are in the in phase part. V is considered here. V is considered here and the lower upper part, and U is considered here in the lower part. And so, the mean value of the V and mean value of the U, where we are interested in, because we understand that finally we will be interested to calculate the symbol error probability. The mean value of this V and the mean value of this U, both of them will be given by this expression, and the derivation of this noise component, following the way we did it for the single carrier communication, we can compute the variance of this the V2 and the variance of U2. Both of them will be governed by half of this N0 by Ts, because the channel duration time and all, because the channel duration time over which the integration is going on, that will play a role. Now, coming to the using the tone interference model that we have done in the last 3 module, we can calculate the error probability of the two parallel symbol streams, as we understand the total probability at the output of this decision device, output of the parallel to serial converter. Here, if we try to consider the total symbol probability PS, it will be a combination of the individual branches error probability, and the contribution should be such that half of the time the error is equiprobable in both the branches. So, it will be half plus half, and actually as they are having a Gaussian distribution because of the understanding of all this expression. So, they will be governed by a Q function, where actually your Es is the symbol energy given by the earlier slide, and NOE will be 0 or 1, I mean it is something L, defining actually the path, upper path or the lower path, and this is the one sided power spectral density, combined power spectral density of the interference plus the noise. And we know that the expression for all this, if we utilize a rectangular chip, that will be governed by this, and this has a direct relation of the expression that we have derived in the earlier modules, where L is coming extra because to capture the effect of the in phase and the quadrature phase component in the cos component, and we will put the 0 and 1 for the value of the L to get actually either the cos 2 pi or the cos 2 pi plus cos 2 phi plus the pi 180 degree out of phase expression for the lower value, for the lower path. Your phi, if you remember, the phi was given by theta 1 plus 2 pi f dt into Ts, and if you have to utilize that Ts 1 is equal to 2 by twice the Ts. So, all this expression should follow that. and the equation indicates what? Finally, the equation indicates that this PS phi for a quaternary system will be given by the total expression of the upper path, error probability of the upper path, and plus the error probability of the lower path, and that equal probable. So, it is half plus half, and the worst value of the phi is usually the lower than the PS phi for the binary direct sequence system with the same cheap waveform and the worst value of the phi. So, if it is usually lower, means the phi of the quaternary system, I mean the QPSK system or any quaternary system which will be lower than this, both of them cases where the binary space spectrum communication system will be utilized. The symbol error probability will be determined by finally integrating this PS phi, by integrating PS phi over the range of the phi, and we will consider that this range of the phi is again will be uniformly distributed over a zone of 0 to 2 pi, and we also understand that cos 2 phi will be having almost all the values within 0 to pi by 2, and going by the logic that we followed in the last module. Here also the integration will be shortened over the duration of 0 to pi by 2, and we have substituted the value from the q side here, from the q function here, and quaternary system in that sense it gives a slightly little bit more advantage relative to the binary system when the tone interference is present, and we will compare the performance of both the symbol error probability for the quaternary system as well as the binary system in the next slide. When actually your FD is will be 0, that means tone interference is been given exactly on the carrier frequency of our interest, and it will be also nearly the same, almost actually if we see that if my carrier frequency tone interference is exactly on the carrier frequency, then only the binary system and the quaternary system will be providing almost the same kind of the performance. And next case what we have done is we have given a symbol error probability versus the normalized frequency offset for both the quaternary and the binary system. What we tried to see that this symbol error probability what we have derived here in presence of the consideration, assuming that there will be a perfect synchronization between the transmitter and receiver and carrier frequency is perfectly transmitted, what will happen, which is not a valid assumption for the practice. If I consider that there is a actually in the system implementation there is a normalized frequency offset in between transmitter receiver, and with the increment of these offsets from the 0 value, from 0 value means the perfect synchronization situation, how both of them will vary. If this is our consideration, we did the simulation or the experiment is done when the gain V is equal to 17 dB and your signal to noise power spectral density, signal power to noise, signal energy to noise power spectral density is given fixed at 14 dB, and this disparate signal to the interference power is considered to be 10 dB. Tone interference is present and FD is considered to be 0. That means, tone interference is present exactly on the center frequency of transmission. What we are varying now, we are not considering that we are normalized, the normalized frequency offset is exactly 0. If it is 0, then both of them will have the exact performance. But if we are having some amount of the normalized frequency offset, we find that the quaternary system has some better performance. It gives a little bit better performance compared to the binary system, and this effect of this improvement basically it vanishes if you are increasing the normalized frequency offset further. So, with this we will try to end up the whole analysis on the whole performance analysis of a direct sequence space spectrum communications. So, in gist over the last 4 modules, so we have learned how actually the jamming signal placed on the center frequency, close to the center frequency, with having some Gaussian interference affects our symbol error probability. And in the last module, we have learned that if we are shifting from the binary space spectrum communication system to a quaternary space spectrum communication system, whether we are gaining somewhere in terms of the error performance. We have seen that compared to the binary systems, in the quaternary system, the performance of the quaternary system will be more resilient with respect to the normalized frequency offset, which is very often you will face when you will design a practical space spectrum communication system. Every time you cannot get the perfect synchronization, perfect estimate of the carrier frequency in the receiver. So, in that situation it will be preferable to go ahead with the quaternary systems compared to the binary system design.